Welcome to Spring LIB.
All right. In this problem, we are looking at cathode ray tubes in two separate situations. In the first situation, we have an unknown voltage accelerating our electrons, but we know that the X-rays produced have a wavelength of 0.15 nanometers. And this is in the ideal case, so this is the minimum lambda in the case where we assume all of the energy of the accelerated electrons is converted into the energy of the X-rays produced at the target. In case B, we're given the voltage of the cathode ray tube, but we need to find what's the best, or rather, what's the minimum lambda of those X-rays that can be achieved using this voltage difference. Both problems will proceed in the same way. We will use two equations. We're going to assume that the energy supplied by the cathode ray tube, the energy of the electrons accelerated by a potential difference, is simply the electron charge, E, times V, the potential difference. It's worth noting that this is not an expression of electron volts. This is the electron charge times a voltage difference in the tube, which gives an energy, which if we assume all the energy is transferred perfectly, this would be it. So this is optimal. And we're also going to need the energy of light, which is hc over lambda. So it's inversely proportional to the wavelength of the light. And we will be setting these equal to each other by assuming that all of the energy from the accelerated electrons transfers to the light in both cases. So the constants we'll be using: speed of light, 3 times 10 to the 8 meters per second, and Planck's constant in its joules seconds form, not electron volts form. Okay, so let's jump into it. It's a rather simple procedure. So if this is the energy of electrons being accelerated in a potential difference, and this is the energy of light at a certain wavelength, we can, by assuming that the energy transfers perfectly, no losses, we can set these equal to each other. Equals hc over lambda. And then depending on what are our unknowns and unknowns, we can solve for whatever we need. So for part A, we're solving for V, assuming that we know what lambda is. So in this case, we just solving for V, we have hc over E lambda. That's our equation. For case B, we assume that we don't know V. We assume that we know V, and we're solving for lambda instead. So then the equation simplifies in a slightly different form. Great. So we've now, depending on which unknowns we have and which we don't have, we can find V or lambda. So for part A, we need to find V, given lambda. So these constants: 6.626, e to the negative 34 joule seconds, 3 e to the 8 meters per second, all over the electron charge, 1.6 e to the negative 9 coulombs, rather e to the negative 19 rather. And we assume that we know lambda to be 0.15 e to the negative 9 meters. And for part B, we have the same situation, same H, same C, same E. But in this case, we plug in a known voltage of 30 kilovolts, so 30 e to the 3 volts. So numerically, let's start with, for part A, after number crunching, we end up with a voltage needed to be 8,282.5 volts. That's what's needed to achieve X-ray wavelengths of 0.15 e to the negative 9 meters, or rather 15% of a nanometer. And then for case B, if we have a V of 30 kilovolts, we can expect, in the best possible case, to obtain wavelengths of 4.14 e to the negative 11 meters for lambda. So these are the results for A and B respectively. It's a relatively straightforward procedure. So thank you very much.